The second most important law is the Kirchhoff's law. They are still relevant despite they were discovered or they were reported some around almost 200 years ago by a Russian guy known as Gustav Kirchhoff. He proposed two laws. One is related to the current, and we call it the KCL or the current law. We call the other one is the voltage law. So we have the current law and the voltage law. Let us see what is the significance of these two laws, and why are these two laws still relevant in electrical engineering. Kirchhoff's current law states that they said that the algebraic sum of the current at any node at any time is 0, while the voltage law says that the algebraic sum of all the voltages around any closed path in a circuit at any time is 0. Now, which means that we have that in any closed path, if there is one unknown voltage available, then we can find out what is that unknown voltage. In the same fashion, using the Kirchhoff's current law, if we know if there is one unknown current in that particular node, that can be calculated. Let us see what they are mathematically, how they can be mathematically expressed. Let us first of all see how we can use the Kirchhoff's current law. The Kirchhoff's current law. So let me make a circuit. So you can see in this particular circuit that I have drawn, just arbitrarily, there is one node here and there is another node here. So let me call this is node A, this is node B. We have a node here, we call it node C. Another node here, we call it node D, and here we have this node E. Further, we suppose that we have currents in these particular directions. Now let us write the convention. Let us understand the convention of writing the equations for the Kirchhoff's current law. So the convention that is widely used in the textbooks, it says that any current entering the node we assign it a is attributed with a negative sign, while all the currents that leave the node, leaving current, is given a positive sign. Now it does not matter if you inverse this particular convention, but you have to stick with this throughout the solution of that particular circuit, otherwise you will not get the correct answer. So let us first of all write, as an example, let us write what is the equation for this node C. We say that suppose that we have this current I1 coming from this side, this is I2, this is I3. So if you see, this I1 is actually entering this node, so we will write it as minus I1, and then these two currents are actually leaving this particular node. So I can say that this is I1 plus I2 plus I3, and their sum should be equal to 0. Similarly, if I want to write for this particular node A, then for node A we have this current, let us say this is IS. This IS is actually entering the current, entering the node. So we have IS with a negative sign, and that plus with this, let us say this I4 plus I4, that is equal to 0, or in other words IS equals to I4. So I can say that because of this particular law, I can safely say that the current entering is equal to the current leaving in any node. So this is what we have in the Kirchhoff's current law, and it can be used to solve some really simple circuits. For instance, let me draw a given let me draw a circuit. So we have, say we have this particular circuit, and we have a controlled current source as well, with a value equals to 1.5 times Ix, where this is the current, which is Ix. We have no information about the value of the resistances, but we will see that it is not actually required to know what is the value of the resistances, because this circuit is a quite a simple circuit. So this is 1 I1, this is 6 milliampere, and this current is known, it is equal to 1 milliampere. So we are tasked to find out in this particular numerical what is the value of the current Ix is unknown, and I1 is also unknown. So let us see how we can solve this circuit by just applying the Kirchhoff's current law. So if we see here, this node is available, and we have this particular node available. So let us apply the Kirchhoff's current law at node A and node B. Now remember that whatever the current which enters a node, we have to assign it a negative value, and all the currents that leave the node should be assigned the positive value. So for node A, we shall assign minus 6 milliampere plus Ix plus I1 equals to 0, or in other word, Ix plus I1 equals 6 milliampere, right? Similarly, I will apply at this node B. Let me apply the KCL at node B. If I apply this node at this node B, then there is this current I1, it is entering this particular node B in this direction. So I can write this as minus I1, and then this 1 milliampere is leaving the node, so that is 1 milliampere, plus this current is also leaving, which is the current of this dependent source. So plus 1.5 Ix, and that is equal to 0. So you can see here that based on these two equations, I have two unknowns, and now it is super easy to solve these two equations with two unknowns. And doing so, I get Ix equals to 2 milliampere, and consequently I1 is equal to 4 milliampere. Now with this thing in mind, let us apply this particular thing on our circuit back. Let us apply it again on our circuit and see if it is okay. So if you see here, if I apply it on this circuit, so Ix is equal to 2 milliampere. So we have 2 milliampere current going in this particular direction, and I1 is equal to 4 milliampere. And this certainly means that the current which is entering this node A, which is 6 milliampere, is equal to the sum of the currents that are leaving this node A, and that is equal to 2 milliampere plus the 4 milliampere. Similarly, if I go on this node B and I want to verify that whether the Kirchhoff's current law holds true for this node, then what I can say here is, I can say that 4 milliampere is coming here, 1 milliampere goes here, and this is 1.5 times I of x, that is equal to 1.5 into I of x is 2 milliampere, so that is equal to 3 milliampere. So we have 3 milliampere going to through this dependent current source. 4 milliampere is coming, and hence this 1 milliampere goes through this particular path of the resistance, and hence at this node B, the Kirchhoff's current law holds true. Notice here that this whole line which is here, which is at this particular bottom here, this all is actually, we can say this is node C. So if I apply the Kirchhoff's current law at node C to see whether it is holding true for this particular node, then what I can say here, that we have 3 milliampere current coming into the into this particular node C from this dependent current source. Then we have 1 milliampere coming from this particular branch of the circuit, and then we have this I of x which is also going into this node C. So I can write this minus Ix with negative 2 ampere, and this all is equal to 3 to 5 plus 1, that equals to this 6 milliampere current source. So we can see that the Kirchhoff's current law holds true for this particular circuit. Going forward, let us see what is the Kirchhoff's voltage law, the KVL, right? Let us see what is Kirchhoff's voltage law. So the Kirchhoff's voltage law, it says that in any closed path, for instance, we have this particular circuit. In any closed path, the sum of the voltage rise and the voltage drop, that is equal to 0. Now the question arises here, what is the voltage rise and what is the voltage drop? Now as a convention, let us say that the current in this particular circuit is moving in this clockwise direction, and we call it I. Whenever the current, if the current enters the positive terminal of any device, we put a plus sign with that voltage, and that is said to be a voltage drop, or in other words, this is the voltage drop. And if the current enters the negative terminal, we use a negative sign and we call it a voltage rise. So for instance, in this particular circuit, I have assumed that there is some current which is flowing in this clockwise direction. It is always sane to follow the conventions which are given in your textbook, and henceforward I have actually used this as a clockwise, in a clockwise direction. So you see this current I is actually entering the negative terminal of this Vs, and hence I will write it minus Vs, and then it is entering the positive of this V1 plus V1, and then again it is entering the positive of this V2 plus V2, and this is equal to 0. In other words, this with the negative sign, this represents the voltage rise, right? Voltage rise, and these two represents the voltage drop, and that is what we studied in the definition of this Kirchhoff's voltage law, that the sum of the voltage rise is equal to the sum of the voltage drop. Now let us say what kind of circuits can be solved only by using this KVL. KVL is a very handy tool to find out the voltage across the 2 points if all the other voltages are known. For example, let me draw a circuit. Let us say this is 24 volt. Then I have 12 volt here. Okay. Then I have a resistance here which has this 4 volt here, and then I have another resistance here. It is in this particular direction, and then we have this plus this is 6 volt, right? Let me label the nodes as well. So this is A, this is B, C, D, E, and this is F, right? So it is desired to find out or to calculate the voltage between points A and E. VAE is unknown. Now how can we find out this VAE using only the Kirchhoff's voltage law? It is very easy. So as a first step, I will assume that there is a connection here, and I call this VAE between point A and E. The second here, as a convention, I will assume that this VA is at a higher potential than this VE, than the point E. So I will write this, give it a plus value and give this a negative value. Thereafter, what I can do here, I will apply the I will assume that a current is flowing in the clockwise direction, and I will write the Kirchhoff's voltage law equation for this particular hypothetical loop. Notice that this VA is not actually the actual part of the circuit. It is a hypothetical assumption that there exists some sort of a connection between point A and point E, and that connection has a voltage equal to VAE. Second thing that we did is that we assume that VA is at a higher potential than this point E. So we put a plus sign with A and the negative sign with E. Now if I apply the Kirchhoff's voltage law here, then the simple answer here is this current is entering the negative terminal, so this is minus 24. Then it is entering the positive terminal of VAE. So I will write plus VAE. Then it is again entering the positive terminal of this particular resistance here. So this is equal to plus 10, that is equal to 0, and consequently we have VAE equals to 14 volt. Notice that the application of the Kirchhoff's voltage law alongside this AEFA path, to solve this particular solution, we can also go along this ABCDEA path, which is shown, which is here. So if I say that we have some current I flowing here with the same assumption that we have A side positive, then starting from this particular side, this is 16, then it is entering the negative terminal, so minus 12. Then the current enters the positive of this 4, this is plus 4. Then it enters the positive of 6, this is 6, and then it enters the negative terminal of this VAE, so minus VAE, that is equal to 0. Now if I sum this up, VAE is equal to 14 volt. So it does not matter what is your choice to apply the Kirchhoff's voltage law. My choice will always be the loop containing less number of voltages in it, so that it is simpler to solve for that particular thing. The another important thing here is that even if you assume that this particular current, even if you assume that this current is in this counterclockwise direction I, even if you assume that thing, it will not hurt the answer. So let us assume that we apply the current for this small path in an opposite direction or in a clockwise direction. So if I do so in this clockwise direction, it will just invert the values here. So this will become 24, this is minus VAE, this will be equal to minus 10, and that is equal to 0. And again you will get the same answer as this one, which is equal to 14 volt. So Ohm's law, so the Kirchhoff's voltage law is very handy in finding out the unknown voltage across 2 points in a circuit, provided that all the other voltages are actually known. So this is one thing. But the most important point, if I summarize these three laws in a nutshell, we have from the Ohm's law, we have that if we know the current through a resistance, we know the voltage and vice versa. This is the straightaway conclusion with respect to the Ohm's law. Regarding the Kirchhoff's current law, it says that when we have only two elements and we know the current through one element, then we know the current in the other element as well. So if we have two elements here, if you know that there is 1 ampere current flowing through this element number 1, then it is imperative that this same current will flow through this element number 2, because if you apply the Kirchhoff's current law here at this particular node, then this 1 ampere current is entering the node and hence it should actually leave the node. So this is equal to minus 1 ampere. So that is equal to 1 ampere. And the third thing here is from the Kirchhoff's voltage law, that if there are two elements connected in parallel and we know the voltage across one element, then the voltage across the other element is also known. So these are the some of the observations of these basic laws. In the next class, we will discuss how we can apply these Ohm law and the Kirchhoff's law together to solve a given circuit. Till then, take care. Allah Hafiz.